A very good day. My name is Sashini Anna Perampuan Maran and I am from 2BEE S1/2. Today, me and my group members, Ephraim, Pugalanti, Rinoshan, Selvantiran and Sharwin are going to be presenting our project assignment for electronic system. For the introduction, an electronic system refers to a tangible collections of interconnected elements or components that enable the integration and organization of various types of information. The topic of oscillators, active low-pass filters, rectifier, and including voltage regulator and load will be covered in this assignment, and a detailed examination will be conducted on circuits belonging to each category. These circuits will be explored in order to gain a deeper understanding of their functioning and characteristics. For oscillator, an electronic oscillator is a circuit that generates a repeating waveform such as a sine wave or a square wave. It converts a steady direct current (DC) from a power source into an alternating current (AC) signal. Oscillators are extensively utilized in various electronic devices. They are responsible for producing signals in radio and television transmitters, regulating clock signals in computers and quartz clocks, and generating sounds in electronic beepers and video games. For the oscillator one positive feedback loop, it is given that the resonant frequency Fr equals to 1 kHz. Hence, the value of C will be assumed as 1 nanofarad. Therefore, the value of C1, C2, and C will also equal to 1 nanofarad. To find the value of R by using the formula and the given frequency, Fr is equals to 1 over 2 pi RC. To get in terms of R, the formula will equals to 1 over 2 pi Fr times C. By substituting the values of Fr and C, it can be obtained that the value of R equals to 159.2 kilo ohms to the nearest standard value. Next, we are going to recalculate the frequency with the calculated values of R and C to determine whether it matches the specifications. Again, the formula is 1 of Fr equals to 1 over 2 pi RC. By substituting the values of R and C, we obtain that Fr equals to 1 kilohertz. Now we are going to take a look at the negative feedback loop. We use the gain formula to calculate RF and also RA. Given AV equals to 3. Then AV equals to 1 plus RF over RA. RF equals to RA, and we are going to assume that RA equals to 10 kilo ohms. RF equals to 2 times RA. Hence, the value of RF equals to 20 kilo ohms. We are going to take RF equals to 20.1 kilo ohms to the nearest standard value. Next, for the measured values, the measured values can be taken from the oscilloscope of output frequency and peak amplitude. Output frequency obtained is 994 Hz, whereas the peak amplitude VPK equals to VPP divided by 2. From the oscilloscope, the VPP obtained is 28.2 divided by 2, hence the value of the peak amplitude is 14.1 volt. Next, we are going to see the multi-sim circuit constructed for oscillator 1. It is shown that this is the negative feedback loop and this side is the positive feedback loop. Now I'm going to run the simulation. For channel 1, we are going to measure the frequency and also the peak-to-peak values. Once the value of the peak-to-peak reaches 28.2, we are going to stop the simulation because this is the highest peak-to-peak amplitude obtained. Hence, the frequency is proven it is 994 Hz and the peak-to-peak value is 28.2. This is all for oscillator 1 circuit.
A very good day. I'm Dinushan from class 2 BEE session 1/2. Now I'm going to present about oscillator 2. So for the first one, positive feedback loop. Given that the resonance frequency FR equals to 1 kilohertz, hence the value of the C will be assumed as C equals to 1 nanofarad. Therefore, C1 and C2 equals to C, that's equal to 26.5 nanofarad. To find the value of R, by using the formula and given frequency, FR equal to 1 kilohertz, that equals to 1 over 2 pi RC. So when we substitute the value, we get the R equal to 300.3 ohm as the nearest standard value. So for the next step is to recalculate the frequency, which is calculated value of R and C, determine whether it matches the specification or not. So FR equal to 1 over 2 pi RC. When we substitute the value, we get 20 kilohertz. So for the negative feedback loop, use the gain formula to calculate RF and RA. So AV equals to 3, AV equals to 1 plus RF over RA. So RF equal to 2 over RA. Assume RA has 10 kilo ohm. So RF equals to 20 kilo ohm. So we can assume as a standard value 20.1 kilo ohm. To find the measured values of output frequency and the peak amplitude can be observed from the oscilloscope. So we get is output frequency F4 equals to 17 kilohertz and the peak amplitude VPK equals to VPP over 2. That is 7.99 over 2. We get 4 volt. So the next is multisim circuit. Okay, this is the multisim circuit for the oscillator 2. And the up one is the negative feedback loop and the down one is the positive feedback loop. As we go to the oscilloscope, when we run the circuit, we get the frequency as 17.0 kilohertz and the peak to peak we get 7.87 volt. So the measurement and the calculation are proven as the same. Thank you.
Assalamualaikum and hi, my name is Muhammad Izzat Shahmi bin Muhammad Azli. My matrix number B0821103880. So in this project, my part is voltage summing. So what is voltage summing? Voltage summing is an n-ohm sum multiple input voltage into one output voltage. It connects the input voltage to the ohm amp, inverting or non-inverting input terminals and choose the feedback network resistor. Inverting summing amplifier setup. This voltage summing setup is typical. Resistor connects the input voltage to the op amp inverting input terminal negative. Each resistor has a summing point and a common end. The feedback resistor connects the output terminal to the summing point. So op amp output terminal voltage is taken. So the next slide. Okay, this is our circuit for this project. Okay, the upper one is a OC first oscillator and the below one is a second oscillator. So the output for the first and the second is connected to the op amp using summing configuration. Based on two input, we get one output. So the output is Okay, so we got for the frequency we got 17.2 kilohertz for the frequency, and the peak to peak voltage we got 4.05 volt. That's all for me. Thank you.
A very good day. Let me briefly introduce myself. My name is Ephraim Simon Rajaram. My matrix number is B0821100057, and I'm from the class 2 BEE section 1 group 2. And I'll be talking about active LPF or low pass filter. This is an example of a filter circuit. So active low pass filter is when they use a OP amp, or should I say operational amplifier, as their main amplifying device, along with resistors and some capacitors. So this is to provide a filter-like performance at a low frequency. Okay, the most common and easily understood active filter is what we have here, an active low pass filter, because it uses this OP amp for amplification and also gain control. So this is the circuit. As you can see, the values I will explain later in the calculation part. So this is the circuit. As you can see, there's resistors, capacitors, and a supply. Then we connect it to a board plotter. So then when you run it, this is the waveform we get. What waveform is this? This is a waveform when this curve here is what we call a frequency response curve. Right, this straight line here until the drop is called a pass band, and then it drops down straight down, and this is what we call a slope. So now go back to the circuit. You can see there is different values. The values is we got the value from calculation. This is the calculation, and for LPF we can see there's a certain table of fixed values. So now we need to find the value of resistor. We find it via the damping factor formula. You can see 2 minus R3 over R4 is equal to 1.1414 here. There's a damping. As you can see, this is in a second order, and this is the first stage. So we get 1.414. By doing normal math, we can see that it is 0.586. So this is the answer for 0.6. You can see it here too in the table. It's 5.86. 0.586. Now then we just assume that R4 is 1K, and then we just do the same thing. We just substitute, and then we can get the answer of 586. And then it's given that our FC is 8K, and use the formula again, and then we assume that the capacitance is at 10 nano ohm, and not ohm, farad, nanofarad, and you can apply the formula, and we get this 1.989 k ohm or 2 k ohm. So we go back and we just applied all this value that we got here into the circuit, and we run to get this frequency response curve. So this is LPF, active LPF or active low pass filter. That's all from me. Thank you.
Hello everyone, a very good day. Here I'm Selvan Kiranarajan from 2BEE section 102. My matrix number is B0821100041. Here I'm going to present about rectifier. What is rectifier? A bridge rectifier is a type of full wave rectifier. A full wave rectifier converts the input waveform to one of constant polarity, as opposed to a half wave rectifier, which only passes one half cycle while blocking other. Here's the calculated value. Our given task is our capacitor value should need to be in 1 microfarad at the output of the rectifier, which is the calculated value we get for the VDC is equal to 12.732 volt, and then the Vout is 18.6 volt, and the V ripple is 204.167 millivolt. Here's our measured value, which is we are using our multi-sim app for the simulation. The VP in value we get from the multisim is 19.9 volt, and the V out ripple we get from the multisim simulation is 3.89 volt. Here's the connection that we are put in multi-sim simulation. Our VPK value is 20 volt and we set it for 30 Hertz. And our V out value, the V in value we connect to the channel 1 and the V out value we connect to the channel 2. And then the capacitor, as our given task, we put it for 1 microfarad, and the resistor value we put it for 100 kilo ohm. Here's the connection of the multi-sim, and here's the output of the multi-sim connection. Yeah, I'm going to show in multi-sim app. So which is as I show in the PowerPoint, the connection all same. And here we go check on channel 1. The channel 1 VRMS, the RMS cycle value is 14.1. And then the maximum output value we get is 90.9 volt. And for the channel 2, the peak to peak value we get is 7.78 volt, as we put in our Microsoft PowerPoint. The VPP value 7.78, and the measure value is we get VPP is 13.9, as shown in multi-sim. That's all from rectifier part. Thank you, everyone.
Hello, my name is Sharvin. My matrix number is B082110, and I'll be explaining the voltage regulator section of our electronic system assignment report. First, we constructed the voltage regulator circuit that we have learned from the previous lab. Then we used 8 volts as the input circuit, as in for the VO from the rectifier. We assume that the value of R1 is 10 kilo ohms, R2 is 1 kilo ohm, R3 is 800 kilo ohms, and R4 is 24 ohms. Then after we simulated the circuit, the value of our VO and PO are simulated almost the same as the specification that we instructed for this assignment. This is the calculation that we have performed for the voltage regulator. We assume that we insert the 8 volt as the input. VZ we get 2.3 volts. Assume the resistance value as follows, as I mentioned earlier, and we will get the power output of 1.048 watts. With the voltage output of 5.015 volts. This is our circuit that we have built and measured, and this is all for my part. Thank you.
My name is Pugulini Manali, and my matrix number is B0821101193, and I will explain about the summation of all specification, discussion, and conclusion. So this is the combination of all the specific circuits. So we have two identical circuits, which is oscillator 1 and oscillator 2. And when these two are connected, it will connect, the output will connect to the summing. And after summing, it will connect to the LPF circuit, low pass filter. And after that, we will connect, the output will connect to the full bridge rectifier. And from that, the output goes to the voltage regulator and load. So this is the combination of all our circuit. So furthermore, for discussion, the oscillators play a crucial role by generating a periodic electrical signal, typically a sine wave, which is essential for converting a direct current signal into an alternating current signal. These oscillators provide the necessary waveform for further processing. To combine the output signals from both oscillators, we employed a voltage summing amplifier, which ensures proper mixing of the signals. In order to modify the frequency response of the filter circuit, we integrated an active low-pass filter. This filter enables us to achieve a more selective output response by narrowing or widening the filter's output bandwidth. By adjusting the filter parameters, we can tailor the characteristics of the filter signal to suit our specific requirements. To meet the DC requirements of the system, we employed a voltage amplifier. This component efficiently converts the alternating current AC into a DC signal, which is necessary for DC operating systems. The rectification process ensures an unidirectional flow of current, enabling compatibility with the DC-based electronic components. Furthermore, to provide a stable and regulated voltage to the load, We incorporated an upgraded voltage regulator, which includes a shunt regulator. This regulator maintains a constant output voltage regardless of fluctuations in input voltage or load conditions. By effectively controlling the flow of current through a shunt element, the regulator ensures the load receives a consistent and regulated voltage supply. Overall, our circuit design incorporates oscillators, a voltage summoning amplifier, an active low pass filter, a voltage rectifier, and an upgrade voltage regulator to enable the conversion, filtering, and regulation of the electric signals for proper functioning of the electronic system. So, as conclusion, by constructing the circuit design for this project, we are capable of understanding the purpose of each block and process involved during the simulation of this circuit. The circuit design consists of two oscillators producing 1 kHz and 20 kHz. Firstly, the low pass signal oscillator dismisses high frequencies. Then signal enters the full wave rectifier with AC voltage to DC voltage. The voltage controller used to generate a fixed voltage, spike voltage, by adjusting RC attached. Lastly, the simulation was successfully constructed by using multisim software. That is it. That is all from us. Thank you.